Hello everyone, thanks for coming. Today I'm going to talk about our paper Makes the Minority Great Again, which is a first-order regret bound for contextual bandit. This is based on the work by Zeyuan Alan Zhu, Sebastian Bubeck, and Yuanzhi Li. So the problem of interest in this paper is contextual bandit. Contextual bandit is defined with k arms and n experts. Usually we should think of as the number of experts being much larger than the number of arms. And at each iteration, each expert suggests an arm. And one way to think about it is the arms are the actions you want to do every day, and the experts are the people around you. For example, your parents, your friends, or your English teacher. At each day, they will suggest you to do something that they believe is good for you. For example, they want you to do more exercise, to drink more water, or to learn machine learning. And at the beginning of the day, we see all these suggestions, and then we pick an arm. And then at the end of the day, we will see the loss of this arm that we pick. And for simplicity, let's assume that the loss is between 0 and 1. And what is the goal? The goal is to be almost as good as the best expert in terms of minimizing the loss. So what does this almost mean? Usually this almost is measured by a regret bound. Let us assume that we have t rounds and the accumulated loss of the best expert is L. So previously there is a result that gives an algorithm called ESP4 that has loss L plus root of tk log n. In other words, this algorithm has regret root of tk log n compared to the best expert. And this regret bound is very good when L is large. For example, L can be as large as t, then root tk log n is a small order term. However, this bound is not so good when L is small. For example, when L is smaller than root t, then we are actually doing much worse than the best expert. So recall that we want to minimize the loss, so L is small is actually the interesting case. So now comes the question, can we actually do better? Can we actually get a regret bound depending on L instead of t? And such regret bound is called the first order regret bound, which is a regret bound of the form root lk times log n. And recall that we assume the loss is between 0 and 1, so L is at most t. Of course, in principle, L can be much smaller than t. So we are actually doing much better. And this was raised as an open problem in last year's code. And in this paper, we give an algorithm with regret bound root of kl times log nt and plus some small order term. So when n is very large, like as large as t or something comparable, then we basically get root kl times log n. So we essentially solve this conjecture. And before presenting the algorithm in our paper, let us just recall the classical algorithm in this field, which is called EXP4. So what is this EXP4 does? At each round, in EXP4 will assign a probability mass over all the experts. Intuitively, the experts will have smaller loss, and the experts with smaller loss will be assigned with a larger probability mass. And then at each iteration, we will pick an arm proportional to the overall probability of the expert suggesting this arm. For example, if we have expert 1 assigned with probability 0.1 by the EXP4, and expert 2 assigned with probability 0.3, and expert 3 with probability 0.6, and we also see the suggestions that expert 1 and 2 suggest arm 1, and expert 3 suggests arm 2. Then we should pick arm 1 with probability 0.4 and arm 2 with probability 0.6. And this 0.4 is the overall probability of the expert, which is 1 and 2 suggesting this arm 1. And what is the regret of ESP4? The regret of ESP4 is root tk log n. So why is that regret? Why does ESP4 suffer that regret? Because ESP4 will ensure that each arm is picked as probability at least 1 over root tk in each round. So why do ESP4 needs to do that? Because it has to control the variance of the estimated loss of each expert. Recall that we only see the loss of the arm we pick, not all the loss. So we need to pick each arm with sufficiently large probability in order to reduce the variance of the estimation and to get a meaningful estimator. However, if we actually pick that arm with this amount of probability, then the regret is at least the root of TK, because we may pick a very bad arm, but at least with this probability. So how do we do better? How do we do a first order regret bound? So in order to do that, we need to reduce the probability mass on those minority arms. So when an arm is very bad, we shouldn't pick it with a very large probability like 1 over root TK. And in the extreme case, we will only pick the leading arm. And this strategy is called the follow the leader. So let us look at this strategy, follow the leader. What does it do? It just says that each arm we will assign a probability mass over the experts, and then we will just pick the arm with the highest overall probability, and we will do nothing to the other arms. And very easily we can see that it's a bad strategy, because each arm can take lead to be the best arm, but the leading arm will always have loss 1 in the next round. So can we improve this strategy? And in this paper, we present a new strategy called the follow the soft leader. And in two-arm case, what does this strategy do? This strategy will follow the leader, or follow the best arm, if the overall probability arm mass of this leading arm is more than 1 minus r for some r in 0.5. So we call this strategy soft R. And in this paper, we present the algorithm make minority great again, which is based on the following crucial theorem. It says that if exp4 has regret much larger than root tk, root lk times log nt, which is our target, so which means that the minority is actually hurting us in this case, then there is a value r such that the strategy soft R has total loss L minus root TK log n. What does this mean? This means that this strategy has even negative regret. It is doing much better than the best expert. So this is a crucial theorem in our paper, and we will use this theorem to show the final regret. So in order to apply this theorem, we have to add some artificial experts, because we don't really know a priority what is the correct value of R. We just know there is a correct value. So how do we do that? We actually design T new soft R expert, and each expert suggesting that picking R equal to I over T is the correct value of R. And then we add those experts to the expert pool, and we run exp4 on the original expert and these two T new experts together. So we show that these new experts are actually self-proving in the sense that with these new experts, exp4 must have regret root of kl times log nt. Why is that? Because if that's not the case, then according to the theorem, there is a soft R experts with total loss smaller than L minus root TK log n. However, because exp4 has a low regret, then this is a contradiction, because the soft R expert is actually doing much better than exp4, and that cannot happen. So we finished the proof. And thanks for listening, and thanks for coming.